Thank you. It's a pleasure for me to share with you about soil spectroscopy in terms of data science, in terms of modeling. So my presentation, my talk will be more focused on the data science part of it, and I will pose some questions and probably some research that that will be of our interest. And if we can take it further later on, that would be great. Okay, so before I begin, I would like to acknowledge the traditional owners of the land, Australia, and I like to recognize their continuing connection to the land, water, and culture. So I'm currently presenting on the land of the Gadigal people of the Eora Nation. I pay my respects to their elders, past, present, and emerging. Thank you. So I will begin. Oh, hold on a second. Oh, a second. So with a bit of nerd. Okay, that's the nerdy bit. So a quiz particularly for Travis, he told me he's interested in astronomy, although this is not astronomy. So which is the first unmanned rover which landed on the moon, and it is equipped with a soil sensor? Is it A, B, or C? Maybe someone can type in the chat box. Anyone? C? Anyone else? No. So the answer is the one with the cool name. It's a Lunokhod. It's a Soviet Union or whatever moon rover, if you call it, because it has although this is 1970, 1970, it only have a lifetime of less than a year. It is equipped with an instrument which is called a RIFMA, which is an X-ray fluorescent. So people been thinking already that back those days. So if we are in the moon or if we are somewhere, how can we collect soil data remotely or proximally in this sense? That means that it's near the ground, right? So there is this kind of thing already happening on the moon, but on the soil, our soil, there is a recent and probably not recent, there's a past 10 to 20 years, people are trying to gather soil information, gather soil information proximally. So can we use some sensors in collecting some data? So this is Omar. Omar is our ex-PhD student. So he's now at University of Lincoln in Nebraska. So he drove around with this rover, and it's not quite a moon rover. It's not quite the rover that we see but it's still manually operated. But what he is doing, it has a sensor attached to it. And so when he stopped, he did this kind of thing, the noisy thing. So as you see, it's very cold out there. So what he's doing is that he's pushing the probe in the soil, pushing a probe through a penetrometer in the soil. And on that probe, it has a NIR sensor, in near infrared sensor. And when the probe pushes on the ground, it collects the signal of the soil near infrared spectrum. So this is an example. This is actually in our Camden farm in the university. So this is the same design that it collects from the surface down to 1 meter. Every 2 centimeters, it collects the near infrared probes. So what we want to understand is that how does this near-infrared spectrum, which is collected on the soil in situ, how can we transform it into soil information about something about the content of the soil, either carbon content of the soil or clay or other things. So this comes the soil spectroscopy data analysis. So particularly in the visual to infrared spectrum, so the soil responds differently to the reflectance of the light in the visual or near infrared or the mid infrared, depending on the literature. This is the band wavelength, yeah, from around 400 to 800, 700 in the near infrared, and then continue to 2500 nanometers in the near infrared, and then further down 2500 to 25,000. That is the mid infrared, because so this is this part here is the mid infrared. It can what people say that it contains the fundamental peak that reflects to the content of the soil, for example, the quartz or the aluminum and oxides bands, and so on, and carbonates and quartz, and the components of organic matter, alkyl or clay minerals. And this is the fundamental band that is in the mid-infrared. So you can see there are prominent peaks in the spectra. But as we go along to the near infrared, this is more, the spectra is more dampened. The peak is not that sharp. It's more broad as well, because it is what they call a certain overtone of or reflection of what's happening in the mid infrared. But the thing is that the near infrared is very robust. There are portable instruments that you can use in the field, and it's less affected by the surface condition, while the mid infrared is more of a laboratory instruments, which I'll talk to you later. So we are looking at time and cost effective methods that is minimally prepared, no chemical reagents required. We get the spectra and we transform it with this some mathematical techniques. And we want to also, within a spectra, we want to predict multiple soil properties with one scan. So we talk about near infrared spectrum, but ideally this how the soil reflects or responds to the electromagnetic spectrum is through the whole entire electromagnetic spectrum, from the radio wave to the gamma wave. We can collect actually the response of the soil as a function of the frequency or the energy or the wavelength. Of course, there are different ways, and in the radio waves, it's more sensitive to the moisture content of the soil. So if you read the literature about the remote sensing of soil moisture using satellite, that is because of the response of the soil to the radio wave or to the microwave frequency that is reflected to the relative permittivity of the soil or the dielectric constant of the soil. And the infrared is more responsive to the mineral and organic materials of the soil. But further down, there's also the X-ray fluorescence, for example, X-ray fluorescence instrument that you can collect data as a function of its energy, because when you irradiate the soils with an X-ray, it gives up the elements in the soil, jumps from one of the orbital to the other and give up energy, which can be measured, that is related to the component or the element of the soil. And further down up to the gamma ray, so in the gamma rays, we are talking about natural emission of the gamma spectrum. We can also detect the amount of components or mineral components of the soil. So we will present more about the infrared spectrum, but spectrum itself of the soil is a more general topic, more generally that is available from the whole of the electromagnetic spectrum. So in mathematical terms, it is what they call as a large P, small n problem. Large P, that means that more variables than the number of data. So within a spectrum, for example, like this, we could have, let's say, 3,000 variables. If the data collects at every frequency, the frequency or wave number, or yeah, like it could be the X variable or the explanatory variables can be 2,000, 1,000 to 3,000 variables, but your data points may be only 100 or 200 or maybe 500. So it's a problem of large P, small n problem, which we describe in this book. It's a joint effort that we provide some basic, this is some basic functions in R. How do we process such data so that we can infer the soil properties? So that's what called soil spectral inference. From the spectra, can we infer some soil properties through mathematical analysis, through mathematical treatments? So a bit of timelines about how things progress. In the 70s, people are looking at what we call as multispectra. That means spectra of the infrared at different bands, at let's say 3 bands, 4 bands in the RGB or RGB and near infrared. So this is mainly to do with remote sensing, the availability of remote sensing either through a plane or through the satellite Landsat satellite. And people are using multiple linear regression or principal component analysis to reduce the dimension of the data. So in the 80s, well, we're going to have more of what we call hyperspectra. That means we have hundreds of variables in the spectrum. And people are talking about creating a soil spectral library. So if we got a library of spectral responses from different types of soil, can we make a library so that we can infer properties from all around the world? So then in the chemistry, it's called chemometrics, and there's a method called partial least squares, which I'll talk about later. And also people are starting to talk about neural networks. And in the 90s, it goes to more digital. So from hyperspectra, now we're talking about ultraspectra. The hyperspectra means hundreds of bands, and ultraspectras, now we are talking about thousands of bands because we can go digital spectroscopy. And there's people start talking about proximal sensing. If we can not remotely by plane, by satellite sense the soil, but we can proximally sense the soil near the ground. So either in a visible or near infrared or mid infrared. And most of the techniques we use are chemometrics in terms of PLS, but they are already, we are using data mining techniques such as neural network, general additive models, or support vector machine. And in the 2000s, people are starting to collect lots of spectra. We want to build a spectral soil library, and we're trying to different machine learning models. And now we have a larger spectral library, and we want to explore techniques used in data science for big data, such as deep learning. So the calibration methods, what we use is to how to convert this spectra into soil properties, what we call as soil spectral inference, is that we need to use the whole spectrum, because in chemistry, we usually observe Beer-Lambert law. That means that the amount of reflectance or absorbance depending on the concentrations, so of a particular peak. But here, because soil is a mixture of different components, the increase in the concentration of particular element does not necessarily translate to the linear incremental in the reflectance or absorbance of particular peaks. So the shape of the whole spectra will be more meaningful to use than a particular wavelength, but people still use reflectance of particular wavelength. So it's a multivariate problem, multivariate calibrations, large P, and the other thing is that it is highly correlated. So the simple solution is dimension reductions into latent variables, or the other way is variable selection. We don't use all the spectra, but we select some of the spectra. So there are methods like linear multivariate methods or machine learning methods. In a linear methods, the simple simple analysis is that you get the spectra predictors. We need to estimate the regression coefficients that if you multiply, it will give you some responses. And one simple way is to do a principal component analysis is that we want to transform the spectra into smaller scores, smaller number of scores, so that we can relate linearly to the variables of our interest. But there's a particular method called partial least squares, which is similar to a principal components. Principal component analysis only decompose the explanatory variables or your X variables, but the PLS regression decompose both the X and Y values into a common set of orthogonal factors or scores, right? So it is this is the spectra. The spectra is decomposed into some score matrix that you multiply by some loading matrix. But this scores matrix also is linked to the variables of another variable, which is to do with the response variable. So in other words, that you try to optimize the decomposition of the one spectra, which not only describe the variation in the spectra, but also have some predictive capability that enable it to predict the response. So it is a multilinear regression problem, and it is used. It is the standard. It's not just in soil science, but in chemistry, as I say, chemometrics. This is still the most used method. Partial least square regression, and in machine learning, people also use it for many other things. And it's considered as machine learning as well. I don't know why, but anyway, partial least squares, that is where it came from. It came originally from analyzing spectral data in chemistry. So we have measurement, and then we got the data, but we need to do some spectral pre-treatment before we do modeling. So usually we take samples and then multiple samples, and then we average the spectra. Sometimes we do from reflectance that what we measure, the light got reflect, how much is it reflectance. Sometimes we do it what we call as absorbance. It's just an inverse relationship. And we do a filtering, which is the common way, is a moving window filter. It's called a Savitsky-Golay filter. Common analysis in spectral analysis in analysis, that it's just a moving polynomial that you fit through the data, and you can take either derivative or other things. And in doing those polynomial fitting, you can already filter the data, and you trim out the parts where there's lots of noise. You trim it out, and you also sometimes scale it. Why do you want to scale it? Because the reflectance, the reflectance is sometimes due to the lighting or different conditions, scanning of the conditions. So you want to standardize it so that it has a mean 0 and variance of 1, so that the spectra is not affected so much on the condition of the scanning. And after this, then you take this spectra. So as I say, you can also do a first derivative or other second derivative, or sometimes people want to enhance the peak so they look at particular peak and then enhance it, and then this spectral, you treat it, and then you do a modeling. And one particular modeling tool that we found that will be that are useful is what we call as regression rules. It's a method called QBIS. Initially, it is a commercial software by an Australian researcher. Actually, he was from Sydney University. So it is a regression tree, but the tree is a rule, so that the leaf, if you call it the leaf is a linear regression then rather than a single number. So you get something like that. which is surprisingly very effective considering you're presenting the machine learning models with 2,000 variables, and the prediction are just single rules based on single wavelength or waveband, right? So when we compare this is QBIS in compared with the standard partial least squares method. There is some consistently better, slightly better, but consistently better. And 3-net is similar to random forest. That was long time ago. But particularly because of partial least square linear regression, there is a tendency of linear extrapolation of a negative concentration, which is not expected. Negative concentration, which is sort of partially remediated by QBIS because it doesn't allow too much of the extrapolation. Okay. So moving on forwards, now we have what we call as a solved spectral libraries. That means that people in the lab usually kept their soil samples. And with this technology, they go back to their library, soil library. So people not only keep books in their library, they also keep soil samples in their library and rescan those samples. And with that, we have what we call a soil spectral library. So particularly the one we work with the USDA Kellogg Soil Survey Laboratory. So they have been doing soil survey for the past, I don't know how many years, 50, 60, maybe 80 years. And each time they collect the samples, they preserve the samples and they store the samples. And the samples are available in the archive. So now they went back to the archive and scan all those samples. Now we have a soil spectral library. So in this case, when we did this analysis, it was a few years ago, there's about 17,000 soil samples. Now they have increased it, maybe, I don't know, 30,000 soil samples. Now it become a big P, big N problem. So we don't have, we have data of a spectra that is about 2,000 variables, and your P and the N will be in terms of 20,000 to 30,000 data points. And I think Jose has told you about deep learning, so I won't go into it. So we look at deep learning. Can deep learning give us something better? And in this case, it's a one-dimensional deep learning signal that we put it in the program. So this is done by Watini and colleagues, and also Mariam, who used to be at the SHI. So this is the structure of the deep learning because it's done by Watini. His name is Warnet. That's a little joke. So, and when we look at the spectra, so we input the spectra of the raw spectra. So we don't do any transformation, we don't do any pre-treatment, but we just input the raw spectra. And through the spectra, we can see that they actually want the convolutional filter already done, the pre-treatment that we talk about. So for example, in this one, from the reflectance, it's already from the absorbance, it's already converted into from reflectance. It converts it to reflectance, and some of the spectra it's converted itself into absorbance, and some of the filter convert the spectra into derivatives, right? So which one are more efficient or what's being used, we don't know. But this is what the convolutional step in the CNN does, is that it does the pre-treatment, what we did previously. And we compare different methods. As we say, this is the partial least square, the conventional method. QBIS is a machine learning method that we talk about, and then this is CNN. And consistently, it is CNN would be better than QBIS and would be better than PLSR. So on average, the CNN is 39% more accurate and 28% more on the QBIS. So this is in terms of visible to near infrared spectra like this. And then if we go on to the more higher wavelength or higher frequency, then for shorter frequency, we got the mid-infrared. So on average, you can see the improvement. So with more information of the spectra, with more peaks that it can pick up, the increase in the performance is observed in all models. But again, the CNNs be able to predict a bit more accuracy than the conventional method. And then we look again. So what if we combine both the near infrared and mid-infrared through the CNN and put it as two different input layers. So the input can be two layers, and we got some improvement, but the improvement is really not much different from the mid-infrared. So I think that if you already have a very high performance, further including further information is not going to help you much further. And the other thing we want to look at is that this multitasking of the neural network. So it can predict multiple properties at once, right? So, but is this multiple properties at once does it maintain the correlation between the properties? And how do we know that it's working? So one thing that we check is that in soil science, we have what we call as a compositional variable. So the sand, silt, and clay, this is the amount of sand, silt, and clay in the soil should add up to 100, right? So we only model the sand and clay in the CNN, and then we predicted the silt as the difference between. So the silt will be 100 minus the amount of predicted sand and predicted clay. And this is the silt prediction without, it's a indirect prediction of silt from the predicted sand and clay. So, and the CNN, I think we can see that indeed there is an improvement. While the partial least square and the qubits, they are all independently predicted. The sand is independently predicted. The silt is the sand is independently predicted, and the clay is independently predicted. So there is a consistent improvement in terms of predicting the silt content, which we don't see in the improvement is much higher than what we see in the prediction of the other. So how does it, is it really a fluke, or is it a by chance, or is it this multitasking? Does it really maintain the correlation of how does it maintain the correlation? It's one thing that we don't know yet, but we know empirically that it makes sense that that it does maintain some correlation of the prediction. There's one thing, one research question related to the CNN that we did long time ago when we revisited, post questions to you. That suppose that we want to predict a function, a curve, right? So for example, don't worry about all this complicated. So this is what we call as a water retention curve, this one, and this is a hydraulic conductivity curve, which describes how water is retained in the soil and how water is transported in the soil. It's usually expressed in some kind of a mathematical function. Don't worry about these functions. And it's and we can say that it's expressed in these parameters. In this case, 5 parameters, 6 parameters that express the water retention curve of a curve. So we want to predict these parameters, right? So we have measurements. We wanted to predict these parameters for a particular soil. So how do we do it? So conventionally, we take the spectra or the soil properties and we predict all these parameters in the fitted parameters in the neural network, for example. But the thing is that this is the fitted parameters, and all these parameters are correlated as well. Can we do something else? So what we did is that this is the predictors, and this is through the neural networks. So this is the predicted parameters, right? So the predicted parameters, we predict the actual measurement values. We predict the actual measurement values. So when we fit the CNN, we are not optimizing the predicted values, but we are optimizing what it can predict, whether the neural network can predict the actual water retention and hydraulic conductivity. So it needs a bit of modification of the neural networks. The neural network algorithm, that you predict one thing, but you're optimizing actually the performance of the neural network in describing, for example, water retention. So we did this just by, because this is a simple neural network, we did this by optimization, and yeah, it seems to work. So if we want to do this in a TensorFlow, or can we do this? Can we modify the structure of the CNN so that it optimizes another thing? Not can we change the optimization problem? So that's my research question for you. And the next thing for the CNN model is, how do we interpret the model? So how do we know how does the CNN work? So we did this by a simple sensitivity analysis, right? So means that this is a spectra, right? So we input the data of a spectra. So, and then for each wave bands, particular wave band. We first calculated the mean of the wavelength, mean of the spectra for the data. So this is one value. So, and then we go through each wave band with particular wave band, and then within that wave band we start the input value of the prediction model of the CNN. Then we start to input different values, but only we start to perturb or change the input value of the particular wave band with what we observe in the training data. Does it make sense? So we make a prediction, but each prediction is the mean value of the spectra. But within each band, we start to perturb the range of the spectral values, and then we calculated how does the prediction change with the prediction. How does the CNN variation in prediction, and lo and behold, that it gives a sort of a response function that says that, for example, in total carbon, this part of the spectra is not being used at all. That means that even if you change the variation in different reflectance of the spectra, is not going to change much of the total carbon prediction. But it's very sensitive in this, for example, in this one and this particular peaks, which we found that this is regions correspond to the fundamental stretching of the aromatic and alkyl and functional groups of organic matter. So it's interesting that the prediction is not that the CNN is using all the bands, it's sensitive to all the bands, but only particular bands that if you start to perturb it, then it starts to change that it is this is a simple way of how we did interpretability of the model. Of course, there are other ways that are more sophisticated, and one way, this is the one that I found, is they look at the weight of the CNN model, and then trying to figure out which are the response of the particular wavelength that are corresponding to the convolutional network, which are more complicated. Yeah, it'll be interesting to see how this compare. I think the only thing that this method does is that it only varies a particular wavelength. It doesn't take into account the correlation with the other, while the prediction, it may be that there are multiple correlation with the other, which are not explained in that one. The next one is this particular example is that, I don't know if you've seen it before. It is in several presentations, several talks. People talk about it, that machine learning and deep learning is at some point, the machine learning with the number of samples, we're going to flatten, but deep learning is going to increase forever. I don't know, is it forever or keep increasing with the number of samples? I don't know who invented this hypothesis, or I can't seem to find maybe you can help me. So this indeed, like in terms of PLS, you can see that with the number of samples, for example, from going from 2000 and 3000, you can't really decrease the error much more from, for example, 2000 to 3000. And then you say that you only need even 1,000 samples to get a decent calibration. The more samples you put in, the calibration is not going to increase your performance of your machine learning. So we try that with the deep learning. But again, this has an assumption that the CNN is a fixed structure, right? Maybe it needs to be adapted as well as you increase the number of data points. It needs to be more complicated of a smaller number of points. It needs to be simpler. But for a particular structure, below 2000 points, the performance is really not much difference with the QBIS and PLS. With QBIS, PLS is large. But above 2000 points, we can still see that we see that the R-square value at least keeps increasing. Whether it will keep increasing if we have more samples, we don't know. So in this data set from Brazil, we only go up to 7,500 data points maybe. Whether increasing the number of samples to 20,000, it will keep increasing. I don't know. And the next, what people are doing is that trying to understand. So now we have this big data library. How do we use this spectral library? So there's some strange concept that that now you have a big spectral library, for example, a global library, local library. So the problem is that if you got this global library, when you try to predict at locally, it doesn't perform well. Why? Because probably it is, when you do a calibration on a large scale, on a large data set, you're trying to generalize the relationship. But on a local scale, on a field scale or farm scale, what you're seeing, the relationship is more specific. So when you use the library of a global library, which tries to generalize the prediction, usually perform very poorly on the local scale. So what people are suggesting is that, for example, this is your global spectral library, and then you add a small number of samples, 10 samples from your local field to this global library and recalibrate your data, and suddenly, lo and behold, then you get a better prediction, and they call it a spiking method. It's crazy, right? So you got a big 10,000 data points, you add 10 points, and then it suddenly performs much better. Do you believe it? It's crazy. So people do this kind of experiment. So indeed, when you compare the root mean square error, what we call as the regional of the larger one, compare with when it's being spiked, when you add a bit of data, then you see an improvement in the root mean square error, particularly when the data you added is 5 to 10% or 10 to 30%, you got improvement like 1 times or 2 times to 5 times more better than if you are doing with the global library or a regional library. So how does it work? So, but when we compare it with making the model just from the local data, making the model from the local data, that data that you tend to spike, it's actually no better than if you do it on the spike regional library. So what the spiking does is just that you're feeding the local data in terms of you're just trying to fit the local data, and then so so what we found is that most of the time spiking the regional or global library is no better than deriving a local model itself using the same number of samples. So what can we do? So in terms of it, there are different options. So people trying to do local model, that means that within the spectral library, you take your data and then you take your spectra and then you compare with the library and then take the nearest, let's say 100 data, the 100 closest spectral library, 100 closest spectra that are closer to your unknown samples, and then build a model and then predict on it. That is, people call it memory-based learning. And then, or the other one we try is that localized regional. That means that we do the principal component analysis using the global data. We do the principal PLS components using the global data, but then we recalibrate it using the local data. So what we call as localized regional. In that case, one way or the other, localized prediction seems to be a better option than doing this spiking. There are, of course, options that Jose talked about is transfer learning. You do your global library and then you fix your convolutional layers, and then locally you can do readjust the other layers. And there's another method that people talk about. This is from a publication recently that they say is a joint calibration. So this is particularly very interesting, that if you got a spectra from different instruments, sometimes, for example, this one, the wavelength are different. Sometimes this one, for example, the Kenyan one has the wavelength starts from 700, while the Brazilian one starts from 500, and the other one starts from 350. So can we still use it together, all of this library? So what they did is that they go through the encoding process, that the spectra is represented in some spectrum and then encoded in some way, so that there is a way of, if you don't have such data, that this is blank, and doing some encoding and so on. I don't understand everything. Then you can do a joint calibration with all these different data sets. And particularly, I think this is useful and in addressing some of the problem, because different labs and different libraries have different labs have different instruments, and each instrument has its own characteristics that make them, they are incompatible, the spectra. So people from this lab and the other lab, if they use different instrument, sometimes the spectra are not compatible. So how do we adjust them? There are ways, of course, that you get the same samples and then you scan on two different instruments, but that's requiring the transfer of samples. But are there mathematical encoding way that allows us to do better? So the next one is that from lab to the field, as you see before. And the problem is that in the field that you have the effect of moisture. So this is the same soil, but we wet it up at different water content. And particularly we see that particularly the water absorption band at around 2400 and around 1400 nanometers, it is depending on the moisture content. So that means that when you go out in the field at different moisture content in the field and you make prediction using the spectral library, which is calibrated in the lab samples, you will get different results. This is just a prediction. On the air-dried soil, you get a good prediction, but as you increase the moisture content, then the model suddenly doesn't work, because it is affected by the fact that the variation of moisture affect what the model sees in the organic carbon prediction. Then we try to do this with a correction, what we call as empirical parameter or orthogonalization. What it is just we need to find a transformation matrix that pre-process the spectra, the original spectrum, into a transformed spectrum, which is not sensitive to the variation in the moisture. So we did this using a kind of factor analysis. So for example, this is the soil, a particular soil at different moisture content, which we see that there's a variation. The variation is due to the differences moisture content, not the variations due to the carbon content. And we transform it in another space where this variation in the moisture is being reduced, right? So there's still some variation, but this variation is being reduced. This is another example. This is varying. The variation is due to moisture, and after the EPO treatment, this is the spectra, which is slightly different, but this is not affected by the moisture content. So when we do the prediction, on the wet samples, and it is not going to be affected too much by the moisture content. Similarly, on a same soil but being wet at different times, we see a good prediction that is not affected by the moisture. So that means that when OMA go out in the field at different times of the different days, at different moisture, and take different measurement at collect spectra at different times of the day, this is what he did in 3 sites, and this is the prediction of the same, not the same soil, not exactly the same soil, because you can't put the same hole again on the different days where they are high moisture, medium moisture, low moisture. The prediction is not going to throw off completely, but it is at least giving you a consistent prediction of the, for example, in this year, organic carbon. That's it. I think we can do some, as the soil spectroscopy offers us with some new way of measuring soil properties. And the research question that is always popping up is, how do we use these global libraries? How do we localize the prediction with the global libraries? How do we harmonize spectra that comes from different instruments or different labs? Do we need to do it? And how do we all apply it in the local field? And in the field, how do we use it more efficiently? Just an acknowledgement who the people who did all the work, and I'm just presenting their work, is Watini, Jose, Omar, and Ho-Chun, and the NRCS people who led us the data. Thank you.